That was easy.
Hi, so I want to talk about what does it mean in a complexity theory sense to have a small amount of space. So specifically, we talked about this class space of some function of n, and that's all of the languages that are solvable with a Turing machine that runs in that amount of space or less. But what I want to talk about is what does it mean to have a Turing machine that runs in less than n space, where n is the size of the input always. So n, of course, is the size of the input. But you may think, how is that even possible? Because we define the space function to be the furthest cell that you visit, right? So if we draw out the tape contents, and let's put some input on the tape, let's say like this. So you may think, okay, well, the tape head is, let's say, right there. And let's say before we even start, the tape head is obviously there. But what happens if we move it right and then we don't, let's say, access this end of the input? Maybe we only do like the first half or something. So you may think, okay, well then the space should be half of the original input here, the furthest cell that we visit. The problem with that is that these cells over here, that WN there, that is a cell that is quote unquote used by the tape even though we don't actually see it. So you may think, okay, well, if I want to say I want to only access a constant number of cells, maybe I only need to look at the first cell and I don't care about the rest of the string at all. Well, then you may think, okay, we may need all n cells here to represent the input properly. And we technically do. But what we're going to do to achieve anything less than n space is we're going to count the amount of work that we do differently. So the input is always going to have n cells because that's what it's defined to be. But what we should think about is what additional space do we use in addition to the input? If we had more than n allotment of space that we're allowed, then that's not really a problem because the input has n cells and we can use whatever we want over here. But if we're dealing with less than n, then it's a problem because we can't represent the input unless we do something different. We're going to count things a little bit differently. Here's how this is going to work. So we're going to have 3 tapes here. So I'm going to do them in America colors. I'm going to have a blue tape, I'm going to have a white tape, and I'm going to have a red tape. This blue tape is going to be what we're going to call a read-only tape. And this is where the input is. And we can move forward and backward as much as we want across this, but we can never change the cells in here. So it's effectively like a two-way deterministic finite automaton where you can just go back and forth and you're not changing any of the cells here, which is fine. So what is the white tape then? So this is what is going to be called the work tape. Whatever we do on here, that is what is going to be counted against us for the amount of space that we're using. And you may think, what is the red tape then? The red tape is going to be the output tape. And what is the difference between the work tape and the output tape? The work tape, you can do whatever you want on it. You can write, you can move left, you can move right, anything that you wish. The output tape, we can't move left. So what is the consequence of this? Is that because we can only move right on this output tape, that means we can never actually see anything that we just outputted. So the output tape is really only for the receiver to receive whatever computation you're going to actually do. It's some kind of conversion from this input here to outputting something here, and then some intermediate computation is done here. So what are we going to consider? The amount of space that we're allotted here based on the space function is going to be whatever's on the work tape. Because the read-only tape, we really aren't going to think about that counting against us, because if you think about it, the only thing that we could ever really do on this read-only tape is observe the cell and move the pointer around. So effectively, we just have a pointer into the original on this read-only tape. So then if we move this this tape head around, then effectively we just have a pointer to this n cell thing. So then the amount of space that's needed to represent this this pointer is going to be logarithmic in the number of cells in the work tape here. Sorry, the read-only tape. So therefore, the amount of space for this thing is big O of log n, where n is, of course, the size of the input. Okay, and then the output tape, we don't care how much that's going to be. That's not of consequence to us. We could consider it, but we're not going to, because the output in general is going to be larger than the input here. So if we talk about less than n space across these two tapes, then it wouldn't really make sense to restrict this to be less than n, because most conversions are going to make the input into an output that's larger. So we're not going to count this against us. The only thing that's going to count against us is this work tape here. So let's talk about what does it mean to be in space f of n, where let's say f of n is little o of n. So little o means strictly less asymptotically compared to n. So like square root n will count, log n will count, anything that's strictly less than n will count. F of n here is the amount of space allotted on this work tape. You may think, okay, what about that log n upstairs? Well, we actually can't really do much better than that, because we need log n to actually index into this input at all. You can't do any better than log n. Maybe the base is better, but in terms of a constant, you can't actually do better than that. You can do less on the work tape, but you can't do log n less than log n to look into the input here. So in general, it makes sense to consider the work tape to when it has log n or bigger amount of space. So let's talk about log n. So we're going to define two complexity classes here. So L is going to be the set of languages where the amount of work tape is log n. Actually, define it this way. We're going to define it as space log n. And NL is going to be space, n space, I should say, log n. Okay, you might think, Ryan, you're in a completely different outfit right now. So what happened was that I recorded this first intro part of the video way back when, and I forgot about it. And so I'm gonna kick off where we left off. So we were talking about these two classes, L and NL. So L is deterministic log space, and NL is non-deterministic log space. So let's give some examples of some languages that are in here. So one example is that all regular languages are in L. So regular languages are a subset of the class L. And the reason is that let's try and investigate what is actually needed to simulate a DFA, let's say. So if we have the tape right here, which is the input tape, so this is the input W1, W2, up to Wn, let's say. And this is, of course, the read-only tape. We have the work tape and then the output tape, if needed. So what do we actually need to do in the work tape? Well, what we need to do is to march through the string of this corresponding to this DFA. So here we have some DFA, so like Q0 goes to Q1, let's say, on input A. What is actually on the tape? Well, it's actually not just the input string. Remember that the ADFA problem gives a DFA and an input string. So it's not just the input string right here, it's also the machine. So let's modify our tape to account for that. So I'm going to move it over. And in blue, I'm going to write the description of the DFA here. Okay, so how do we actually figure out whether or not this DFA accepts the thing? Well, what we need to do is we need to keep track of the current state and what the current character is. But how do we actually know what character we're looking at? because it could be that like this first character is an A, let's say, and then there's another A way later, or they could even be next to each other. So what we actually need to do is to record the position on the tape where the tape head would have been. So here, I'm going to have a tape head that's right there, and as we're going through the string, I'm going to have the tape head start at the beginning and work our way over. The machine actually doesn't work this way. We need to actually simulate it in a particular way. But this is the idea. We have the tape head here, and as we keep going through the string, we not only keep track of where this guy is, but also what the current state actually is. So the actual tape head is going to have to go from the beginning here, find where that position is, and then eventually go back to find what the state is, and then look up in the transition function over here where to go next. So the things that we're going to record on the work tape are the position of the tape head, which is going to be this purple guy right here. We also have to record the current state, and at the end we need to eventually look up what the actual final state is. So we also need to keep track of where the actual tape head is. So the position of the actual tape head. Why do we need to do that? Well, we are going to be looking up in this DFA right here what to do next. So we actually need to know where we are in the actual tape. And the thing is that we could account for that, but this actually won't change a whole lot, and we'll see why. But the basic idea is we're keeping track of where we are. We're also keeping track of where the DFA's computation is, starting at W1 and working its way through. And we also need to keep track of the current state because I don't know what transition to apply next, obviously. Okay, so how much space does this actually take? Well, the important thing is that we're going to work in binary or a base that's larger than 2. We're not working in unary. Why is that important? Because if we want to represent some number n, let's say, in base 2, let's say base 2, it actually won't matter in the end, then the size of this number written in binary is going to be logarithmic in the actual number itself. So the size of this thing is going to be big O of log n. In fact, you can even give an exact answer. It would be like log base 2 ceiling or something. But it's going to be definitely some constant times log n. So the position here, you may think, okay, well, this n corresponds to that n. That's not necessarily true. This n is the length of the input of the DFA, but this n down here is the length of the whole input right here, including the DFA. But since the DFA has non-zero space, this is going to be even better. We have more room than this one. So that's not really a big deal. So this position right here is going to be logarithmic, or at least the size of it is going to be logarithmic in the size of this whole thing, which is the log of the size of the input, which is what L actually is. The current state, well, that's just a certain portion of the tape. We could just put right here what the position on the actual tape this thing is. So this is just another pointer if you think about it that way. And then the actual tape head is obviously another pointer. So here, all that we actually need to keep track of are 3 pointers. And each of them are logarithmic in size. So since we have a constant number of pointers, all of which are logarithmic in size, that implies that the total amount of work that is done right here is going to be logarithmic in the size of the input, which I think is pretty dang cool. We actually didn't even need the output tape, which is actually pretty interesting, because all that we actually need to do at the very end is to assess whether the current state that we're in is a final state. And then all we need to do is just make a comparison with the set of final states that are written right here in the input. And you can actually compare the 2 pointers, the values of the 2 pointers, in logarithmic space, which is actually all that we need to do here. And so therefore, every single regular language is in logarithmic space. We showed before that you can actually do it in polynomial time, but here we can even do better, which is logarithmic space. And what we'll see is that logarithmic space is a subset of polynomial time. But I want to give you an example of a language that is not regular, but nevertheless is in L, which is 0 to the n, 1 to the n. So this is the famous non-regular language, and I want to convince you that this is in the class L, so it can be solved in logarithmic space. So the usual algorithm to solve this is, let's say that we have our 3 tapes right here. So we have our 3 tapes. We actually don't even need the output tape since we're not actually going to be outputting anything. We're just going to be accepting or rejecting. But let's say that we have our 2 tapes, the input tape and the work tape. So the input, let's say, is 0, 0, 0, 0, 0, 0, 1, bunch of ones, and then blanks after. It actually doesn't matter if there are blanks after because this is read-only anyway. Okay, well, the naive algorithm is just to cross off a 0 and then cross up a 1 and then just go zigzag back and forth. And this is totally fine for the amount of time it takes because we have unlimited amount of time. The problem is that we actually need to record where these x's are. And there's actually a way to get around that. So you can actually use this method using logarithmic space, but I'm not going to go into that. The simpler way of doing this is we have this extra tape lying around, whereas in the single tape model, we didn't have that before, which is actually a benefit in this case. How is it a benefit? We can actually solve a superset of this problem, which is equal numbers of zeros and ones in any order using what we're about to do. But we can also solve this problem in exactly the same way. So what is the idea? What we're going to do is we're going to have 2 counters. So the first counter is going to be the number of zeros written there, and then the second counter is going to be the number of ones. And then all we have to do at the end is check if these 2 numbers are the same. And since these 2 numbers are logarithmic in the size of the input no matter what happens, therefore we are good. Even if the string is all zeros, then we must have that this number, because it's written in binary or a base larger than that, must be logarithmic in the size of the input, even if the whole input is zeros. So in general, these 2 numbers are logarithmic in the size of the input. And so now we're back to reducing to, we have 2 things that we want to compare against each other. Well, we can do that in logarithmic space by doing the back and forth thing. So the algorithm of crossing one off and then crossing off the other one, we can do that with these 2 because they are logarithmic in the size of the input, whereas this input is linear in the size of the input. And so we can keep track of what things have been x'd out using these 2 because they're logarithmic in the size of the input. And so this language is in L. You can actually extend this in the exact same way to 0 to the n, 1 to the n, 2 to the n. And then now we have a language that is not context-free either, but is nevertheless in L. Okay, I want to talk to you briefly about the path problem. So here we have a graph G and 2 vertices, which I'm gonna call S and T. And where G is a graph, where there's an ST path. There's a way to get from S to T. So there's actually a very important subtlety here, which is not really evident here. There's a difference, or at least we conjecture that there's a difference between a undirected graph and a directed graph. So what I'm going to do is I'm going to make 2 versions of this problem. And what I'm going to do with the second one is I'm going to make it yellow so that we can tell the difference. And so the first one I'm just going to leave as is. But the second one I'm going to call DPATH. And this one is, I'm going to enforce that it's a directed graph. So why is this such a big deal? The path problem has actually been shown to be in L. And this is what is called Reingold's algorithm. We may get to it on the channel, but it's a very, very in-depth paper. It's about these things called expander graphs, and I don't want to get into it here. This is just an introduction. But it's in L. It definitely is in L. DPATH, we do not know whether it's in L, and it's conjectured that it's not. But I can show that it is in non-deterministic log space. So how do we actually show that it's in non-deterministic log space? All that we do is we make a set of non-deterministic choices. So let's outline how this works. So we have the input right here and the work tape right here. The input is going to be the graph G, and then S, and then T. Well, what we're going to do is we're going to make a set of non-deterministic choices. So at the very beginning, the choice is the start vertex S. And then all that we need to do is make a set of non-deterministic choices of what vertex to go to next. So let's say that the guessed vertex is V. Then what the machine has to do is make sure that there is a directed edge from S to V. So here we would actually need to store the pointer into the original input right here. So let's say there's a pointer there. So it's looking at this S initially. Then what it has to do is go back into here, and with the second tape head, because there are two tape heads in this thing, because there are two tapes, it needs to look at, okay, this is the starting vertex of the directed edge, the candidate one. I need to use the first one right here to look up in my set of directed edges to see whether or not this is the starting vertex of a directed edge that goes to V. So it looks up in, say, like the adjacency list corresponding to S. Then it goes over to this vertex right here, and it will look at that particular entry and see if it actually is there. If it's not in the adjacency list, then it's not an edge. And so therefore the algorithm can reject. But if this thing is an edge, then we are good. The problem is I can't just keep writing vertices down right here. So what we're going to do is we're going to forget about S, move this V over, and then start over with that. So my new starting vertex is V, and so we'll carry the algorithm on until we either reach V or it produces an edge that is not an actual edge. And if there is a way to get from S to T, then that implies that the non-deterministic choices will make the right one. So eventually we will get to T in some amount of time. I'm only using logarithmic space here because I'm only storing a constant number of pointers. And so this is in non-deterministic log space. If there is no S to T path, then it's impossible for this thing to have made a choice that leads to V because there's no path from S to T under that assumption. And so the non-deterministic machine will actually have to crap out at some point. And also, the way that we can actually verify how long this non-deterministic thing can run before it actually ran too long is we store here, additionally, the number of vertices. So this is just a counter. When we look at when we're given the graph right here, we determine the number of vertices, and that's how long the algorithm has to run. We, for example, every time we do this edge checking thing, we subtract 1 from this number, and if it ever reaches 0, then we've explored every single vertex of the graph, or at least we've ran for the number of vertices in the graph, and therefore we must have repeated a vertex. But the non-deterministic thing would have found the vertex T, in that number of steps anyway. And so therefore we can conclude that we will never see the vertex T and we can reject as a result. And so therefore the directed path problem is in NL, but we conjecture, for what we're going to see in the next video, that the DPATH problem is not in log space. So we're going to conjecture that DPATH is not in log space because we're going to eventually talk about NL completeness. And it's the analogy of P and NP, but for log space. So hopefully that was interesting. Leave comments down below about log space and non-deterministic log space. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.
That was easy. That was easy. That was easy.